everyone. Please confirm that you can hear me. All right, so I guess you can hear me, right? I don't have a way of seeing how many people. Yeah, cool. Are on. And just a couple of more minutes and then I'll start. Hello. Just a minute longer. Hecko. I guess it's a typo. So, guys, awesome. Hello. So, the lectures that follow today's and next week's will be on operating systems theory. And they will be weird for the simple fact that I don't have an English documentation. So my suspicion is that foreign students who actually needed English documentation are back home due to this virus. No, you didn't. But oh, stop it. The documentation is in Romanian. Should you need English documentation, I can provide something that is structured differently. You'll find the notions, but I'm going to follow this. And this is the book that I showed to you first or second, I think in the first lecture, and I told you that this book doesn't exist anymore, and in fact, it doesn't really exist on paper. But these are the PDFs. I'll upload them all, and you can use them as a reference. Should you really need it in English, let me know, and we'll figure out something. Okay, we're going to go a little bit on Mars, but not too much. Great. Okay, so let's get going. I'll go a little bit through the first file, not a lot of it. I'm not going to cover a lot of it. I'll leave some of it to you to read. And then the most part of the class will be in the second one. Okay, oh, that's even funnier, coming soon. Great. Okay, so let's just start a little bit with the classification of the operating systems. Now, this book is not new, so some of these things are not exactly aligned with today's landscape, but it's not that far either. So if we are to look at operating systems from the perspective of how they share resources and how users and processes can coexist, we can look at the older operating systems, such as MS-DOS. I'm not sure you've seen one of those, but you can visualize as the Windows command line, not PowerShell, the CMD, on the whole screen, right? It was just that. No users, and a single program could be run at a time. Very simple, but very popular at the time. So this is something that you call single user, single tasking. These are simple operating systems. You don't do a lot of stuff simultaneously on them. So they don't require so much complexity in their implementation. Then you can have systems that are still single user but support multiple tasking. And well, you can look for that in your, let's say in your Android, right? The Android on your cell phones will only have a single user, but it will support several tasks. So that would be in this category. And then you have the very popular multi-user systems, which is everything Windows, Linux nowadays. multitasking, you can run multiple things at the same time. If we are to look at them from the perspective of how you interact with them, pretty much all these categories, save for the last, applies to what we have today as Windows or Android or iOS. But the first one is a little different. It's not something that you see every day. This one, it's the kind of system that you don't really log in and do things with it. You pretty much submit a job, meaning a program, and the data, and then it gives you back the result. That's it. So I've seen systems like this some long time ago, but they would exist even today. Basically, you have high computing power. This was like a big cabinet with 64 processors and some terabytes of RAM. And you wouldn't really log into a system like this to open VI and do things necessarily. This is not really for users to play on. This is to run computations. So the way this worked, it turned out that the biggest users of this were from the agricultural department who needed to run some simulation of how soil would evolve depending on weather conditions. And this actually meant that they had simulations that were running for days. So these guys would simply submit, here is the data, here is the program, run it, give me back the results. So this is the serial, let's say, kind of interaction. They might run multiple jobs at the same time, but the thing is you don't really interact with them. You just submit the job and you get back a response. Uh, well, that's a nice perspective. Yeah, something like what's in the printer. Indeed. You give it the job, it gives you back a paper. Great. Thank you for that. Now, the rest of them, time sharing systems, this is what happens today. You have multiple processes, each of them gets a little quanta of time on the processor, and practically the processor time is shared among processes. This is common nowadays. Personal computer and workstations, well, this is what you're using right now, unless you're on a phone to look at this. Uh, Embedded systems, these are everywhere nowadays. Your coffee maker will have one. It will not really be a full-blown operating system, but it will be a little thing that acts like an operating system. Sometimes it will even be a full-blown operating system in there, like a small Linux. Then the portable systems, your phones, there is no point of mentioning more about it. And then network connected. Well, this is new actually. This wasn't really a thing until uh, well, by the time when I was a student, this started to become a thing to have network computers. Until then, you just have a computer and it would sit on your desk and you would do stuff on it. But if you wanted to transfer data, you'd have to use like a floppy disk or later on a CD, but not really network. Oh, you're wondering how you debug a program like that? Well, they would debug them ahead of time on their workstations on smaller data. And yeah, if it goes for days and it comes up with bad results, then you have it's hell. But you'll probably learn more about this in your last semester. I think you have a class on computer science history. It's something lighter meant to free a little bit of your time when you prepare your graduation thesis, and you'll learn a lot about those times. My father actually, he was programming on paper with a pencil, and then would give the program to somebody to type it, and that somebody would give him back one or more boxes of punch cards, 3,000 punch cards in a box, each punch card being an instruction. You drop the box, your program gets mixed up, your lines of code mix up, right? And then you take the big boxes to the operator, and then you come back in 3 4 days and you get you get a stack of paper with the results. So there was no F8 and debugging back then. It would be mostly analyzing outputs and figuring out what you did wrong. Totally different experience from what you're having today. All right. So yeah, I'm tempted to click this link, but that would just make us all look at the movie, and I don't know what it is, and I'm not gonna risk it. Okay, so let's look at operating systems from another perspective, from the perspective of their internal, from the perspective of their internal organization. So you can look at monolithical operating system, and that's what you have today in Linux or Windows. These are monolithical, and this means that the operating system is just a large program that starts when your computer starts, and then this program handles everything else, running other processes and so on. And it's called monolithical because everything is part of it. So, for instance, and this brings some risks. For instance, drivers for devices would run as part of the operating system, as a part of this monolith. So when you install a driver, often it asks you to restart. Well, it asked. Nowadays, the architecture changed, but they asked you to restart so that they would reload this driver and it would run just along the monolith. Now, if the driver had bugs, your whole system would come down crashing. So monoliths are problematic like that. Then they came up with microkernel operating system structure. It's a famous exchange between Linus Torvalds and Andrew Tannenbaum. And Linus Torvalds was writing Linux. Uh, Microphone, guys. Do you have problems hearing me, or are you just enjoying jokes? Let me know if you have problems hearing me. Oh, it's fine now. Okay, buzzing. All right, let me know if it buzzes more. I'll restart it. Hopefully, it's not gonna happen. I'll even get closer to the laptop. Maybe that makes a difference. So, a microkernel system is a little different. It really has the operating system is mostly a dispatcher transferring messages between different components. Drivers would be components in this architecture. So then, if a driver fails, um, you don't really have the whole thing coming down crashing, just that driver crashes because they are separate instances communicating. Whereas in a monolith, it's just one big program, a piece crashes, the whole thing crashes, right? Then you may look at this, this, this would be the BIOS, right? It's a small operating system. It's just an interface to the hardware. You can think of it as the BIOS. It's not really an operating system, but it still powers up the hardware and you can do things with it. All right. So with that, I'm just going to stop classifying operating systems. And I just want to go, because I have to select what I can teach from here under these conditions. I'm just going to go and start talking about processes because this is what we will be doing today. And I want to touch on the states of a process. What happens to a process in the system? So when you start the process, that process begins in a state of hold. Now, this state of hold is not very visible today. And also, please understand that this diagram is extremely simplified to only show essential things that we need. And most of them you deal with, right? But if you go in the book, and I'll upload the whole thing, you'll find a much larger diagram with the actual states of a process. Complete fills up a page and it's really dense, right? But for our purposes, this is good enough. So you start up a process and it goes into hold. Now, hold would be very visible with operating systems that take jobs, because there will be a time between you send the job, right? Between they receive the job and then they actually start it. So that would be the hold time. For us, you could regard the whole time. It's hard to say. Practically, you started. There may be a very small moment before the program gets loaded, between you hit enter and it gets loaded into memory, right? So when you start it up, the program gets loaded into memory from the disk. And once it's there, it's ready for execution. Ready for execution means it can get the CPU and start doing things. Now, when it gets the CPU, and it gets the CPU from the operating system, from the scheduler kicks in every now and then and looks, okay, what processes do we have here? All right, we'll give the CPU to this one. So then that one goes from ready to run. And then after a while, the operating system kicks in again and says, okay, I'm going to take off the CPU and you are going to get a CPU. So it moves back from run to ready. So there is a lot of switching back and forth between ready and run for all processes. Yes, this is about the kernel. Actually, not so much. The scheduler would be part of the kernel, and but the process states is something that the kernel sets, yet they're of the processor, of the process. And then you do ready, run, ready, run, ready, run, and at a point the program is finished, so it goes into the finish phase, where all resources are deallocated and cleared. If you didn't close your files, the operating system takes care of them. Allocated memory frees that up as well. Now there are two other states which are on the side, which require a little more discussion. So if you just go vertically, you start the program, you get CPU, you wait for CPU, you get CPU, you wait for CPU, and the operating system chooses when you get the CPU and when you don't, and then you're done. However, during the execution, while in the run state, you may make operations like read from a file, read from the console, write to the file, or maybe lock a mutex or a semaphore. These are operations that will result in the process not having anything to do for a while. When you talk about locking a mutex or a semaphore, this is evident. If it cannot get it, then it has to wait. For I/O operations, which are much more frequent than mutex locking usually, for I/O operations, it's the same thing. But this is not because the process would need to wait for something. It's because it does an operation which is really slow. When you read from a file on the disk, well, the disk is about thousands of times slower than the processor. If it's a hard drive, if it's a solid state, an SSD, it's going to be faster, but still significantly slower than the processor. So then, when you say give me this data from the disk, then you would wait thousands of CPU cycles until the data arrives, and those would be wasted. So the scheduler decides, well, if you're doing an I/O operation, I'm not going to have you occupy the CPU for no good reason. I'm going to move you off the CPU and let others work until your data arrives. So this is the state of wait. If you do an operation that requires just doing nothing until it's completed, and these are usually I/O operations or locking, the scheduler moves the process automatically in a state of wait. When the operation is completed, meaning the data has arrived or the mutex is free and can be locked, the operating system brings it back in a state of ready, right? So from wait, it goes back to ready, from where the scheduler will give it CPU or not. Let me see you guys, because you write a lot of stuff and a lot of it is just jokes. Yeah, that's a joke. All right, so I'll ignore you for a while. Okay, So let's see a little bit about this weight. I just want to make a parenthesis so that you get an idea of what you're working with. Hard drives are slow because they are mechanical. And okay, wait, we have a water addict. The number of processes in run state at any given time can be only the number of threads. Yeah. Well, well, yes, but then you have the question, well, I have a process with multiple threads. So when I say the operating system, the scheduler chooses a process, that may be actually the main thread of a process or any other thread. You can think of threads, actually. It will choose some of them. And you cannot have more than the computation units that you have on your on your host, although in some cases you may do, depending on the CPU architecture, you may do operations in parallel if you have, sometimes there is a coprocessor or the floating point unit can work simultaneously with the integer calculation. So it's hard to say. If you go down to assembly level instructions, some of them will be in parallel just because the hardware allows it. But you can think indeed that you'll only have as many threads active at a time as many computing units you've got. Yeah, or cores. How does the scheduler select the process? Well, there are algorithms for that. We'll discuss of them a little bit. They're quite complicated. And let's see, what are you saying? Normally, threads created, as I've taught you, are by default configured to compete for CPU at the system level. Meaning, if I have two processes, each of them with many threads, all the threads of one process will compete for CPU with the threads from the other. But you can't configure a thread to only compete for CPU with threads from within the same process. There are all sorts of optimizations that you can try. But the operating system has, you could think of it as a queue. It will have a data structure where it has records of all the threads and processes. And then based on their priorities and all sorts of other considerants, it will choose the next one to execute. It may be a very simple scheduler, but then you'd have problems of fairness, or a very complex scheduler that tries to solve a lot of concurrency situations. So let me just go a little bit more about this hard drive thing. So I just want you to understand what you're working with. A hard drive is mechanical. You can visualize it, or you can search on Google for open hard drive images to see what's inside. You can visualize it as like 3 CDs or 2 CDs on top of each other, right? And spinning as one, and on both faces of a CD, you call this plates. So on both faces of this plates, you can read data. And you read it how? You have a mechanical arm that slides a reading head across these plates. So if you need a certain file from the disk, you actually have to position physically the plates and the fork such that they read the data from where you want it to be read. And this is slow. And it's actually, it varies in performance depending on many things. You can, again, search, I think you'll find it on YouTube, something about yelling at hard drives. It's an interesting movie, a little video where a guy in a data center puts up some graphs with hard drive read performance, and then yells at the hard drives, literally turns back to where the hard drives are and yells at them. And then you see the graphs showing a decrease in performance. And that's because vibrations from the yelling affected the positioning of the fork on top of the plate. So when you do an I/O and talk to a hard drive, you're in for delays, and you don't even know how much they will be, right? So that's why you put the process in a state of wait, because you don't know how long it's going to take. It may be really long, and you want to use your processor for something else. With SSDs, it's a little better, but they're still slow. Yeah, the hard drives would need to focus. Poor things. And we're yelling at them. All right, let's move on the right-hand side to the swap state. Now, this state appears when you filled up the memory, the RAM memory. And this is not very common nowadays. Memory is cheap, you can buy a lot, but if you really insist, you can start up a lot of programs and get your memory filled up. And when the memory fills up and you still want more memory, the operating system will try figuring out which areas of memory are not so popular, and it dumps them on the disk, on the hard disk. In Linux, this is done in a partition which is called swap. In Windows, in a file which you will find in the root of the C drive, if you configure Windows to show you all the files. And that file is called pagefile.sys. So these are disk locations meant to receive memory content temporarily. Now, when you start swapping memory to disk, things become really slow. Because if you have two processes and one needs memory and the other one is moved to the swap, but then the user wants the one that's in the swap, you have to load it back into memory and put something back in the swap. So this thing becomes really slow. The laptop will crawl, or the computer. And a process that is moved to the swap, either entirely or partially, enters in the state of swap, from where it returns into a state of ready when there is memory available. Oh, is it pretty common on Linux? I haven't noticed any of that. I haven't noticed Linux crawling because of swapping. They use the swap for certain things, but that's not what I'm talking about. Okay, so this would be the simplified states of a process in execution. Now there is here a operating system structure diagram, which I will skip over. Well, you don't have issues if you have 16 gigs of RAM, but just play with really large programs. You'll see. Install a copy of Oracle there and load up a huge database and do really weird queries. You'll see how it goes bad. Or any database. Okay, so I'm going to skip over this this diagram. I will want you to read it and understand it. It will give you a good view of what's inside the operating system. And I will also want you to read this part about booting an operating system, which I will also need to skip because I cannot cover the whole thing. Yeah, I got it, Alex. And I will switch to this part about processes. And we will look into Deadlock, into Semaphores, and scheduling. So let's see. Most of what you have here is actually, it's not new. We organized this class starting with the practical parts of it. We sort of trained you to be able to use the command line in Linux so that you can do C problems, and you've seen a lot of this already. For instance, what I'm talking about here is a race condition, a way in which if instructions are ordered in an unfortunate sequence, your data gets corrupted. And you've seen this. You see this n minus minus here or here is the same thing that you've seen with threads. So I'm not going to go over that. We're talking about critical sections, critical resource, race condition. And we're also given an algorithm devised by Peterson, but we don't expect you to actually know it, but it will be useful to read about it. Now I'm gonna move to the semaphores, but this will be theoretical semaphores, and I want to go a little bit into this because you've seen semaphores being used. You have the semi-neat, sem-wait, sem-post, right? The semantics of the semaphore operations are you initialize it with a value, and then when you do sem-wait, you reserve a position from those values. When you do sem-post, you release it back. If you initialize the semaphore with 1, it's going to be a binary semaphore and it will work just like a mutex with wait meaning lock and post meaning unlock. But the actual basis of semaphores have been created by Dijkstra. And let's have a look at what's inside. A semaphore is actually a pair of a value and a queue along with two operations. Now the value of semaphore is clear to you. It's the same as you have it in the thread API. It's what you initialize, right? You set it to 1, it's a binary semaphore. And then the queue, it's a simple queue where we will keep track of the processes waiting at the processor, at the semaphore. The two operations called P and V, thanks to the Dutch origin of the author, and I'll let you figure out how to read these names, right? P is actually equivalent, is the same as wait. P will try to reserve a position. And V is the same as post. It will release a position, right? So you have operation P and operation V on a semaphore S. And let's have a look at a simple sketch of how their implementation would go. And it would be like this. We have process A that calls operation P on semaphore S. Okay? So P being equivalent to wait and same trying to reserve a position, we'll start by decrementing the value of the semaphore. And then once it decremented the semaphore, it checks whether the value is smaller than 0 or not. Now, if the value is smaller than 0, that meant that before decrementing it, VS was 0, so there is no more space. So if it's less than 0, there is no space in the semaphore, and we have to wait. Which means that we set the current process state to wait, we set A to wait, and then we record it into the semaphore queue just so that we know that it's waiting for us. Well, at this point, you have process A who's putting itself to wait, right? What should it do next? It cannot execute anything. So then it simply passes control to the dispatcher, to the scheduler, sorry. So A figures out it has to wait, places itself in the semaphore queue, marks its state as wait, and just activates the scheduler. And the scheduler will choose another process, not A, because A is in waiting. However, if the value is not less than 0, it means it doesn't have to wait, so it just, the control is with process A, and process A continues execution. Now, when you perform a V operation, which means unlock, you basically increment the variable, the value of the semaphore. And that would be all, really. You don't need to wait. You're just releasing it and go. However, you need to check, because if the value is less or equal to 0, that means there are processes in the semaphore queue waiting. In which case, you pick one up from the queue, you set its state to ready, and you call the dispatcher, the scheduler. And then the scheduler will choose who goes next. Maybe A, maybe B, maybe another process in the ready state. However, if the queue is empty, so V of S is greater than 0, then A just continues working. So this is, if you want, what happens inside the semaphore when you call wait and post, meaning P or V. Please let me know if there are questions here. All right, so then let's move on to, well, you have here an example of protecting a critical resource with a semaphore, P and V, P and V. This is familiar to you because the semaphore is initialized with 1. This is a binary semaphore, so this is actually equivalent to lock and this one to unlock. Now, I'm moving to the producer-consumer problem, which some of you may have done in the seminar, but I insist that you read it here and understand it. You have seen this usage of semaphores already. It's exactly like we used it for playing X0, I believe. I think we've done that. This kids game where processes needs to give turn to each other, and we've done there this cross lock unlock. You see it? So in the producer consumer, the same issue is presented in a more abstract way. Tic-tac-toe. Is that? Yeah, I guess that's tic-tac-toe. Yeah. Yeah, we use mutexes. This is a little more abstract because we're talking not about what we did in tic-tac-toe is equivalent to only one at a time, but here we're talking about a buffer with a certain size, n. And if you think of it, what you see here is a suggestion of how you implement a pipe using a buffer. So please read this, understand what's going on, and then come to the consulting hour if you need to ask questions or ask your instructors in the lab or seminar. Okay, we're gonna skip over this, and we're going to the reader-writer problem, which we've talked about with read-write locks, and we are reaching the deadlock part. So let's talk a little bit about this. Now you've seen deadlocks already. You've seen them in action. Program just locking up, or maybe two programs locking up. You've seen this when opening FIFOs in the wrong order. But I just want to give you a broader perspective on deadlocks. So there are a few aspects that you need to get. Deadlocks are not really happening very often, unless you're really unlucky. Deadlocks are behaviors of perfectly correct programs that, when running simultaneously, end up in a very wrong situation. If you want, let's have a look at this picture here, okay? That kind of explains it very well. So imagine this is New York, right? And these are blocks. And these are really long cars. Maybe I should put some lorries, tractor trailers. And this is a situation, if you look carefully, none of the cars can move. They're stuck there forever. And this is theoretically possible in any city. however, is very unlikely. Yet, if the traffic is really jammed, you may end up in a situation like this. Now, us being human and impatient, we would not sit there forever. Somebody would drive on the sidewalk, it would figure out a way of fixing us. But these are processes. Processes don't know how to take shortcuts and do anything else than they're programmed to do. So if these were processes, they would sit there forever. And there is another aspect that you need to understand. If you were a driver at the wheel of a car, of one of these cars, you wouldn't really know the situation you're in. You wouldn't really know that you are there and waiting forever. You'd simply wait for this guy to pass so that you can move on. And naturally, you'd expect, well, it is crowded, but it will go any minute now. Had you have, had you had the overview that we have looking from above, you'd know it's never going to happen. And this is very typical to what happens with processes. Processes do not have a perspective of the landscape of what's being executed. They wouldn't know that, yeah, I want to log that mutex, and there is no way I'm ever going to get it because whomever has it needs the mutex that I'm holding. They don't have this information. So they will wait forever. All they will know is that, okay, I have somebody in front of me, they will go away anyway, any day now, and I can continue. So in this situation, a deadlock doesn't really give you much options. Whoever is in the deadlock will just wait forever, and all you can do is pretty much stop them, as in kill the process. And here is an example of how a deadlock would happen, and you've seen it. If you remember, we had a little example where you would pick random positions in an array, lock them, and swap their values. And because these random indexes that we generated were not always in the same order, we would get a deadlock. And the solution was, and I want you to remember this because you'll have to deal with it often enough. The solution to avoid a deadlock is to choose an order for your resources. Doesn't matter what it is, just choose one and always lock them in the same order, and then you're safe. You know this already, but I'm going to look over it from a more theoretical point of view. So for now, let's move on. I'm going to skip this example because you've seen it. There are three aspects to talk about when it comes to a deadlock. How do you get out of it if you were unlucky enough to get it? How do you figure out you're having a deadlock? How do you determine it's a deadlock? And then what can you do to prevent it? And you already know the answer to the first and third aspect. To get out of it, you pretty much have to kill a process, or maybe all threads, because you're going to kill the process and if the threads are deadlocked. So getting out of a deadlock is pretty traumatic. You have to choose a victim. Now, if the deadlock happens in the operating system, right, in the kernel, then you pretty much have to reboot. There is no other way. If it's a deadlock between processes or threads, usually it's enough to choose a victim, stop it, and the others will continue. Fine. Or you can just kill them all. In the case of the cars around the block, it's enough if you choose one of these and tell it, go back a little bit, back up 20 yards. And then the others will move, and when this will come back, it will be all fine. The deadlock would have dissolved. But with processes, you don't really have the tools to say, go back 20 instructions, go back to the state you were in. In some cases, you have this. You make a checkpoint, a save point in the execution of your program, and you roll back to it. But it's not very common. So usually you just choose a victim, you kill the process, and then the others will move on. You restart the process, and things should be all right, unless you end up again in a deadlock. A gentler solution would be if you had this kind of save point or checkpoint and only roll back one of the processes involved in the deadlock to a previous state, which is very much like choosing a process and killing it. You're just reverting it to the initial state. When you restart it, it will be just like this one. So you either go back with the process a little bit or you go all the way, in which case you actually kill it. But logically is the same action. And here I just want you to know that there is another beast hidden, um, which is called live lock. So deadlock is when everybody is stuck and waiting. But now you may say, all right, let me choose a victim. And you choose this victim and you have it back up 20 meters, hoping that while it goes back, this will start moving. But it may happen that when this car comes back, it recreates again the same situation. And then you choose another victim and you tell it to back up. When it comes back again, it's stuck. And this is called a live lock because things are not stuck. They're moving, but they're not progressing anywhere. Oh, yes. So keeping checkpoints would affect memory, but depending on the situation, you may keep diffs, as in you mark all the memory occupied by a process, and then whatever changes, you make copies of it, right? So you may reduce the impact on memory, but depending on what you're doing with it, it's not going to matter much, maybe. So live lock will come when you roll back a process, and when it comes back, it's still stuck in a deadlock, and you do it again and again, and that process is not stuck anymore. That process is working, but it's not progressing. So that would be a live lock. Okay, so we know how to get out of a deadlock. How do we figure out that we have a deadlock? Because this is important. In certain situations, if you don't know it's a deadlock, you don't know how to deal with it. So I'll give you an example. I was involved in developing a system. It was a few good years back. It was a system that was used in the U.S. in car not dealerships. I think it was car like repair shops, and the program worked fine. And then we started getting reports that around 7 in the morning on the East Coast, the program would freeze up and it would have to be restarted. And this was like a central server that they were connecting to over the web. And around 7 Eastern Standard Time, it would lock up and they would have to restart the whole thing. And this was really weird. Why at 7? Yeah, Berzent, I'll get to it. I just want to give you. Oh, again, is it scratch again? Every now and then I lean back and I'm a little far from the laptop. Maybe this will help. Uh, so this guy's the client said, look, something is really wrong. We can't. This is not acceptable to have the program lock up all the time. Figure it out. So there was a team of 30 or 40 testers in the US. They couldn't make this happen. They couldn't replicate this situation. If you can't replicate the bug, there is nothing to fix. You're just stuck in a very frustrating situation where the client says it's wrong and you cannot make it happen wrong so that you fix it. We here were about 4 people. We had no chance of replicating this error. So the deadlock is not really something that happens often. To have it happen, you need to have enough agglomeration, enough concurrency, enough contending for the resources, and then it will show up. So we spent quite a good amount of time looking for it. It was weeks, few months. And eventually we figured out we knew it was a deadlock, we just didn't know who was involved in it. And later we found out that the application container had this feature. If you sent it signal 3, kill -3, it would give you out a report, and we could see there that that we had a deadlock, and we saw the threads involved in it, and we solved it in 2 hours. But it was horrible. And what we determined that was happening is that it was a really weird deadlock. You had it was a combination of United States time zones, uh, working hours of these employees, and the duration, the expiration time on a session not used. So somehow all this came into play, something like the following. You know, people never log out of their websites. So what we had, this was a little older technology, that's how we inherited. So we had something that said, okay, if the user is not using its session for about 8 hours, we kill it. So it just happens that the workers in California, which are 3 hours behind New York, they were going home, never logging out of the system. And then their sessions started expiring when the guys in New York came to work. So then we had hundreds of sessions expiring, and at the same time, hundreds of sessions being created because the New York guys were logging in. And in this mess of expiring sessions and sessions being created, there was enough concurrency for the deadlock to happen. And only in this situation, so there were about 700 sessions going back and forth, and that's when you would see the deadlock. But we had no